So what I want to talk about today in this video is I'd like to go ahead and talk about the squeeze theorem. The squeeze theorem. And the way I want to illustrate it is I want to go ahead and let's show it this way. So let's say I've got three functions. I've got the function f of x. I've got the function. I want to do this one in blue. I have the function f of x. I have the function g of x. Oh, these are really big. Let me just tone it down a little bit. Oh, whoops. Let me just tone it down a little bit. So I have the function. I've got the function f of x. I've got another function g of x. I'm just color coding them right now so you guys can understand. And another function h of x. So let's just say that g of x is like the middle function. What I mean by the middle function is that it's smaller than h of x, but it's bigger than f of x. So maybe h of x is doing, maybe it's coming up like that, it's doing stuff like that, and then it's kind of coming up like that. And then f of x, let's see, f of x is, or g of x, or yeah, f of x maybe is down here, going down like that. Maybe it's coming up, doing some little squiggle things. It's coming up here, and then it's popping down like that. And then g of x is in between those two. So it's kind of just trucking along like that. Let me try that again. It's trucking along like that, coming through there, and continuing on kind of like that. So what the squeeze theorem basically says is that if the limit as x approaches a of f of x, so let's make that right there, that's a, it's got some value L. So if the limit as x approaches a of f of x is equal to the limit, oh, wrong color, the limit as x approaches a of h of x, which all happens to equal some number L, as we showed right here. So the limit of f of x is here in blue, the limit of f of x is equal to the limit of h of x, which is equal to this number L, then g of x, the limit as x approaches a of g of x has to equal that number L. It just has to equal that number L. We proved it graphically here. F of x is the smallest function, as you can see here. H of x is the biggest function. At this point, both f of x and h of x, they're all approaching this same value L, and so g of x must have that same limit, as you can see here, because as we come in from the left on both of these, we're coming in from the left, and we're coming in from the right. The left-hand limits and the right-hand limits are equal. They're both approaching this point, and g of x is forced into the middle of these two. They're squeezed, hence the name of the squeeze theorem. They're squeezed. They're stuck in between these two functions, and so it has to have, at that point, it just has to have the same value for the limit as f of x and h of x, assuming both of their limits exist. So to illustrate how to use the squeeze theorem, I want to go ahead and show an example problem. So I've got an example problem right here. We're going to show that the limit as x approaches 0 of x squared times the sine of 1 over x equals 0. So let's go ahead and solve this real quickly here. So a lot of you are thinking, well, the easy way to show this is to just, use a product property with limits and just say that the limit is the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine to the 1 over x. Let's just do that, happy dandy, and we can find and show that this is equal to 0. Well, here I beg an interesting question for you, because we can directly substitute 0 in here and we get 0, but what happens if we directly substitute 0 into the sine of 1 over x? We'll get the sine of 1 over 0, but 1 over 0 does not exist. You can't solve 1 over 0. You cannot divide by 0. So therefore, because this does not exist, sine of 1 over x does not exist, we actually can't use the product property in this case. So we're going to have to use a different idea, and I suggest that we use the squeeze theorem. Now, we're not given 3 separate functions and asked, oh, what's fun, use the squeeze theorem and stuff like that. We're not given 3 separate functions. We're just given one function. But maybe, based on the knowledge of what we know and what we know about properties of what make up this limit, we might be able to make our 3 functions. So let's take a look. Let's just analyze this function and see what we can find. All right, so here's what I'm thinking. I am recalling my trig properties, and I noticed that the sine function, so the sine function, no matter, I don't care what's within the sine function, but the sine function in general is constrained between the values of -1 and 1. Like that, the range of the sine equation is from -1 to 1, so the sine function has to be contained between -1 and 1. Now, I think you would all agree that if I were to just, let me space this out a little bit better, the sine of 1 over x has to be constrained in between the values of -1 and the values, the value -1. Sorry, I guess -1. Haha, wrong spot. This would be 1, and then back here, this would be -1. Now, I think that you all would agree that if I were to multiply across by the same constant, like if I just multiply the same thing across this whole inequality, you would agree that I'm not changing the value of this inequality because I'm doing the same thing to each part of this inequality. So I'm not actually changing the value of it. So let's go ahead and then, so I'm going to multiply everything by x squared because I wanted to try and associate the sine of 1 over x into x squared. So that way I can do that. So now let's go ahead and simplify this inequality. What are we going to end up getting? Well, we're going to end up with -x squared is less than or equal to x squared times the sine of 1 over x. There's our function that we had before. There's our original function, which is less than or equal to x squared. So there's our original function right there in the middle. Well, that's good. We might be able to use the squeeze theorem as long as we can show that we can tell that this is the middle function. This is the so here we go. Here's the smallest function. Here's the middle function. And here's the biggest function. So if we can prove that the biggest function's limit is equal to the smallest function's limit at 0, then the limit as x approaches 0 of x squared times the sine of 1 over x is going to have to equal 0. So let's try that. Let's see what happens. Well, what is the limit as x approaches 0 of -x squared? Well, in this case, I think direct substitution is going to work just fine. So we're going to plug in 0. 0 squared is just 0. Doesn't matter if the negative's there or not. 0 is just 0. And then what is the limit as x approaches 0 of positive x squared? Well, again, we can just do direct substitution. Substitution works. Directly substitute 0 in. We get 0 squared. That's just 0. I noticed that the smallest function's limit is equal to the largest function's limit. I noticed that the limit as x approaches 0 of x squared, -x squared, is equal to the limit as x approaches 0, the limit as x approaches 0 of positive x squared. So therefore, I can make the conclusion that the limit as x approaches 0, well, that was a bad x and a bad 0. Well, let me just rewrite all that. The limit as x approaches 0 of x squared times the sine of 1 over x has to equal 0. And so that's how you can use the squeeze theorem. So we learned today in this video, that's how you can use the squeeze theorem. That's where if you're given a function and you're asked to show a limit, you don't know what to do. This is an application of how you can use the squeeze theorem to find the value of a limit.